I'm Phoebe Lewis, a supplemental instructor for Dr. Byron Quinn's Natural Science Biology 1 course at Langston University, and I've compiled a series of review videos that will help you with your final. This review video is going to talk about Chapter 10. Remember, Chapter 10 was meiosis. So first we're going to hit on the differences between mitosis and meiosis, the two stages of meiosis, and focus on the fact that genetic variation occurs in meiosis 1. We're going to talk about the causes of genetic variation, crossing over, which occurs in prophase 1, and independent assortment, which occurs in metaphase 1. And then we're going to briefly discuss gamete formation, oogenesis, and spermatogenesis. So first, let's talk about mitosis and meiosis. Remember, mitosis is what all your autosomes or somatic cells go through. These are all of your cells except for your non-sex cell chromosomes. So you're going from the diploid number to the diploid number. Two daughter cells, exactly like the mother cell. And so you're going diploid to diploid, of course. And what it's going to, in mitosis, you remember we got two daughter cells that were exactly like the parent cell. Okay? Exactly like. So this is your skin cells, your hair cells, so on and so forth. All of your cells except for your sex cells. Well, meiosis is a little different. The only cells going through meiosis are your gametes. And so in meiosis, we're going from our diploid number to our haploid number. Remember, haploid has basically half the number of chromosomes as the diploid number. You can kind of see diploid die, haploid half. That's a good way to remember it. So remember, in meiosis, you're going diploid to haploid. And then what you're going to end up with is four daughter cells with half the number of chromosomes as the parent cell, and they're going to be genetically different. And so these are, like we said, the only cells that go through meiosis are your gametes or your sex cells, your sperm cells and your egg cells. So let's talk about meiosis. Okay, meiosis occurs in two stages, and if I'm going too fast, feel free to pause it, take it all in, rewind it. You can do that, right? You might want to write something down. Just go ahead and do that. But, okay, let's review real quick. Meiosis occurs in two stages. Meiosis 1 is the stage that genetic variation occurs. So this is how you may have brothers and sisters and you guys don't look exactly alike, even though you guys may have both the same parents. Well, the reason why you guys don't look alike is because of genetic variation. So there are two main causes of genetic variation. And remember, meiosis is broken up into two stages. In the first stage, it's similar to mitosis, prophase, metaphase, anaphase, and telophase. With this slide, we're only focusing on prophase, metaphase, anaphase. Well, the big things to realize is that crossing over occurs in prophase 1. And so that's where the homologous chromosomes, you get one set from your mom and one set from your dad, and they're going to twist up and form tetrads and exchange genetic information. And so crossing over, which we'll discuss here, I have a better slide to show you, that occurs in prophase 1. The other important thing that occurs in meiosis 1 is independent assortment. Now, independent assortment occurs in metaphase 1, and it just all focuses on how these homologous chromosomes line up at the metaphase plate. Again, we'll have a better slide to show you exactly the significance of that. Now, in anaphase 1, this is an important part that I want you to guys remember, is that in anaphase 1, we are pulling apart, but it's the homologous chromosomes pulling apart. If you go back to your mitosis notes, you'll know that it was the sister chromatids that are pulling apart. So these little sister chromatids right here are pulling apart in mitosis. But in meiosis 1, it's the homologous chromosomes pulling apart. So just remember that, and you might want to go ahead and write that down. And meiosis 2, it occurs just like mitosis. So this is the end. We didn't get a chance to have enough room to show it on the other side. But at the end of meiosis 1, we get telophase, of course, where you have the two distinct nuclei, and then cytokinesis occurs. And what you have is you have two haploid daughter cells. Well, these two haploid daughter cells, because in meiosis, you're having basically two divisions. One replication, two divisions, that gives us four daughter cells. So in telophase 1, we're going to start off with two haploid daughter cells, and these two haploid daughter cells are going to divide, and it's going to end up just like mitosis. So you have the prophase 2, of course, metaphase 2. We don't have no crossing over occurs in prophase 2. No independent assortment occurs in metaphase 2. In anaphase 2, however, it's the sister chromatids that move apart, just like mitosis. See, before we had the homologous chromosomes pulling apart. Well, in mitosis 2, we're going to have the sister chromatids moving apart, just like we learned in mitosis. And so, ultimately, what we're going to end up with is 4 haploid cells. So the haploid cells are going to have half the number of chromosomes as the original parent cell that we started off in meiosis 1, and they're each going to be genetically different. As you can see here, none of them are exactly the same. They're each genetically different, and that is due to the genetic variation that occurred from crossing over in prophase 1 and independent assortment that occurred in metaphase 1. So let's further elaborate on this genetic variation and the causes. Well, we have a thing that we talked about crossing over. It occurs in prophase 1, as I mentioned several times before. Well, crossing over just occurs when you have a duplicated chromosome. So we have homologous chromosomes from our parents, some from our dad, some from our mom. And we have sister chromatids right here. Well, what happens is that these non-sister chromatids may link up and cross over, exactly as the name implies, and form a tetrad. And so ultimately what we're going to have is we're going to have these chromosomes are no longer what we had started off with. We don't have the pure mom chromosome and pure dad chromosome. What we end up having is homologous chromosomes that have exchanged genetic parts. And so this is called genetic variation. And this is responsible for genetic variation. It's called crossing over. Independent assortment was the other is also responsible for genetic variation, and this occurs in metaphase 1. And so it all is a matter of probability, if you will. So it's going to determine how exactly they line up at the metaphase place. So depending on how these chromosomes line up, these homologous chromosomes line up, you see we have two different scenarios right here. The reds are on opposite sides, the blues are on opposite sides, and over here you have the reds on one side, blues on the other. Well, depending on how they line up, it will determine what we end up getting in what our 4 daughter haploid chromosomes will look like. And so that is just a matter of genetic variation. Responsible for genetic variation, that's called independent assortment, and it occurs in metaphase 1. Alright, so the other important thing to focus on with meiosis is the fact that only gametes undergo meiosis. Remember, reminder, gametes are your sex cells. And so this is how your sex cells are formed. This is how your sperm are formed. This is how your eggs are formed. And so, as you can see here, if you have 2 X's, you know that makes a girl, an X and a Y makes a boy. And so let's talk about this. That was just a brief diagram to kind of show you the basics, but specifically let's go over the gamete formation. So you have spermatogenesis. Genesis, just like the first chapter in the Bible, is telling you how everything is formed. Spermatogenesis. Oogenesis, how your sperm are formed, how your eggs are formed. Okay, and so what we have in spermatogenesis is that we start off with a diploid cell, a spermatogonium. The spermatogonium differentiates into a primary spermatocyte and goes under meiosis 1, forms secondary spermatocytes. Goes under meiosis 2 and forms the spermatids. So what you end up having is 4 haploid spermatids, or the sperm cells that all men have. So the spermatids are your sperm cells. Well, oogenesis is a little bit different. You start off again with the diploid oogonium, and it differentiates to the primary oocyte. After meiosis 1, you're going to get a secondary oocyte, and you're going to get a polar body. A polar body is eventually going to degrade. And then you get, after meiosis 2, you get 1 egg and 3 more polar bodies. And so what ends up happening, the differences that you need to understand is that in spermatogenesis, you start off with 1 diploid spermatogonium, and you're going to end up with 4 haploid sperm cells, or spermatids. Oogenesis is slightly different. You're going to start off with 1 diploid oogonium and end up with 1 egg cell, 1 useful egg cell, and 3 polar bodies. And so, as you can see, 1 oogonium does, as in meiosis, it does produce 4 things. It's just that these 3 polar bodies aren't useful to us. We don't have enough material to make a full egg. We only have enough material to make 1 egg. So, oogonium, 1 diploid oogonium, 1 egg. Spermatogonium, 1 diploid spermatogonium, 4 functional spermatids. So that's all you really need to know for meiosis. Rewind this video if you need to. Go over the parts that you were kind of fuzzy on. Take some notes. You might want to write that down. Alright, and that covers chapter 10.